So welcome everybody, and I am very happy to introduce the next talk by Malabika Pramanik. Her talk is on some properties of sparse sets survey, and she is from University of British Columbia in Canada. This will be a recorded talk, but she is available to answer questions during the talk. Thank you.
Hello, everyone. It is a pleasure to be with you today. I would like to thank the International Mathematical Union and the organizers of the ICM for their tremendous efforts in hosting this event and their decision to pivot to a virtual format amidst rapidly evolving circumstances. It is a great honor to speak at this truly global celebration of mathematics, knowing that anyone can join free of charge from any corner of the world. I work in mathematical analysis, specifically Euclidean harmonic analysis and its many applications in geometric measure theory, fractal geometry, combinatorics, and several complex variables. My talk today is based on certain problems in these areas, the common underlying theme being that they all involve the study of sets that are sparse or thin in some quantifiable sense. Here is a rough outline of the talk. It has three distinct components. I'll start by describing a set of problems that got me interested in this area. I will try to explain a little bit about the history of these problems, what is currently known, why sparsity is a relevant concept, and what are some of the big challenges and open questions. A few landmark results will give a sense of the surrounding literature with the understanding that many others exist that could not be cited due to time constraints. Some of these omissions have been referenced in the conference proceedings. The second part of the talk will introduce a few definitions needed to describe some of my own recent work, joint in part with co-authors Yu Liang and Benjamin Bruce. The last 10 minutes of the talk will be devoted to a small proof that does not require a lot of build-up that we can enjoy together. Let's get started. The overarching question in the field of sets and configurations is simple to state. Knowing some rudimentary information about a set, such as its size or some mild structural property, what can we say about the patterns or point configurations that lie within the set? To rephrase, does a small or sparse set contain a prescribed configuration? Must every large set contain one? The sets that we will consider reside in Euclidean space, but other variants have been considered in the literature as well. Clearly, there are words in these questions that need clarification, such as thin, large, and configuration. I have highlighted these. Depending on exactly how these words are quantified, the answers can be positive or negative. The different results fall in three broad categories: existence, avoidance, and abundance, terms that we will expand on in the next few slides. What is a sparse set? These are sets that are small in some quantifiable sense. If a set is finite, then smallness can be measured using cardinality. A set with 2 elements is clearly smaller than a set with 10 elements. For infinite sets, cardinality is too crude a quantification for our purposes, but there is a dizzying array of more sophisticated notions such as measure, dimension, density that aim to capture various aspects of size. We will touch upon a few of them today. So much for size. What about configuration? In principle, a configuration could be any prescribed set. Such a set could be geometric, for example, specially arranged points on a line, or the vertices of a polygon. A configuration could also be algebra analytic, such as zero sets of functions, like non-trivial solutions of a polynomial equation or a system of such equations. Such solutions are called polynomial patterns, linear if the equation is linear. And indeed, there is a wealth of results in all of these categories. Let us look at a cartoon picture to get a general sense of the problem. Suppose the set under consideration is the collection of blue dots here. Based on inspection, the set does not appear to have any special characteristics. Now, let us bring a configuration into the picture. The configuration that we have chosen here is this 3-point set, the 3 vertices of an isosceles triangle. One possible pattern question could be, does our set of blue dots contain a congruent copy of this isosceles triangle? Equivalently stated, are there 3 points in this blue set that exactly match this triplet of red points, possibly up to translation and rotation? An alternative could be asking for a similar copy rather than a congruent copy. Here we allow dilations in addition to translation and rotation. In light of this, let us try to reformulate our earlier questions in a bit more precise way. Suppose that script F is a family of patterns or configurations. Really, it's just a collection of measurable sets, say in the d-dimensional space of integers or reals. Let capital E be an arbitrary measurable set in the same ambient space, though not necessarily in this collection. We'll say that script F is represented in the set E if there exists a member capital F of script F that is contained in E. We say that the set capital E avoids script F if E does not contain capital F for any member F of script F. This gives rise to some natural questions. What is the largest size of a set capital E that avoids script F? Size being interpreted in one of the many ways mentioned before. Second, what can we say about a collection script E of sets if every capital E in script E is to contain some member capital F of script F? As I mentioned before, answers to these questions come in a variety of formats. I have broadly classified them into 3 categories. The first one is called avoidance. Fix a pattern, such as points in progression or vertices of a geometric shape, like a parallelogram. Somewhat counterintuitively, it turns out that there can exist quite large sets that manage to avoid all affine copies of such patterns. The second type of results is called existence. This is perhaps the easiest one to understand. After all, large sets are large because they contain many points. Surely these points must form some classes of patterns. So what are they? Indeed, certain results in the existence category says that the class of patterns contained in a large set is quite substantial in the sense of measure, even though you may not always find the pattern that you are looking for, as suggested by the avoidance category. Or it may be true that large sets under extra assumptions may contain what you are looking for. These kinds of results fall under the auspices of the existence category. The third category is yet another surprising class of statements called abundance. The results here can be in two directions. It turns out that there are really small sets which manage to contain plenty of patterns in spite of their sparsity. On the other end of the spectrum, there are large sets that not only contain many configurations, but actually contain all sufficiently large copies of them. For each of these three categories, I have included an extremely incomplete list of authors who have worked in these areas. Some examples of each of these result categories is in order. Let us start with some landmarks in the existence category. A truly foundational result that has launched immense activity in many directions of mathematics is Zemeride's theorem. Incidentally, this is also a result that makes use of a notion of size called asymptotic density mentioned earlier. Let capital E be a subset of the positive integers. Given any large integer capital N, consider the proportion of the first capital N natural numbers that is in E. The asymptotic density of capital E is by definition the limit superior of this proportion as capital N goes to infinity. Zemeride's theorem states that any subset of integers with positive asymptotic density contains arbitrarily long arithmetic progressions. Let's recall that an arithmetic progression of length k is a set of k equally spaced points. Progressions are among the simplest examples of linear patterns, a k-term progression being given by k-2 linear equations. Let us also mention an example of a nonlinear pattern in the integers, originally due to Furstenberg, later sharpened by Sarkozy. It says that if capital E has positive asymptotic density, in this sense, then it must contain two distinct elements x and y, whose difference is a perfect square. To summarize, both Zemeride and Sarkozy's theorems are existence results, the former for a linear pattern and the latter for a quadratic one. What about avoidance problems? What happens for progressions in sets of zero density? On one hand, there are classical constructions of Salem and Spencer, and also Berendt, that demonstrate large subsets of the integers that are progression-free. On the other hand, there are also large subsets of integers with zero density that do contain long progressions. Examples of this are random sets, as shown by Kohakawa, Luchak, and Rodel. These are sets where elements are chosen to belong to the set using a random mechanism, like flipping a coin. Another famous example of a zero density set with arbitrarily long arithmetic progressions is the set of primes, as shown by Green and Tao. All the examples that we have seen thus far are in the integers. Let's turn our attention to the real line. Is there an analog of Zemmeredi's theorem in the continuum? It is a classical result in measure theory due to Steinhaus that all finite sets are universal. To break it down, what that means is that given any finite set, capital F on the real line, and any real set E of positive Lebesgue measure, there exists a translation parameter X and a non-zero dilation parameter T such that X plus TF is contained in E. On the other hand, here are two examples of avoidance and abundance. Mate shows that there exist very small, in fact, zero-dimensional sets E containing affine copies of all finite sets. There are other results that show that for every finite set F that you choose, there exists a full-dimensional set E that avoids affine copies of F. Steinhaus's theorem admits an enticingly simple proof involving just the Lebesgue density theorem that I will omit here. The simplicity of that argument leads to a natural question. What about infinite configurations, capital F? This stunningly simple question remains one of the notorious open problems in the field, called the Erdős similarity problem, one of his problems stated in the Scottish book. Erdős hoped that there was no such set. He also announced a $100 cash prize for it, which must be one of the hardest ways to make $100. Erdős's conjecture states that every infinite set must be non-universal. In other words, there exists a set capital E of positive measure which does not contain any non-trivial affine copy of F. Non-universality of infinite sets has been verified for slowly decaying sequences like 1 over n, and for certain kinds of some sets, but the conjecture remains open in full generality, and in particular, it is not known whether the geometric sequence is universal. This brings me to the conclusion of the first part of my talk. The second part is a discussion of some of my recent joint work. Let me start with some definitions needed to set the stage. The next few slides are given over to a brief recap of some notions of dimension. Most of these are well known to the experts in the field, but let us refresh our memory before heading out to the statements that make use of them. Critical to many problems in geometric measure theory is the notion of Hausdorff dimension. Its classical definition is via Hausdorff measures. Given any Borel set, capital A, in n-dimensional Euclidean space, consider all possible countable covers of A by balls of radii at most delta. Look at the infimum of the quantity summation Ri to the power of S, where Ri denotes the radius of the ith covering ball. The S-dimensional Hausdorff measure of A is the limit of this infimum as delta goes to 0. The Hausdorff dimension of A is the threshold value of S, below which the S-dimensional Hausdorff measure is infinite, and above which the S-dimensional Hausdorff measure is 0. Alternatively, by a classical result known as Frossman's lemma, it can be expressed as the supremum over all exponents alpha, such that A supports a probability measure mu obeying a ball condition of order alpha, namely, the mass that mu assigns to any ball is bounded above by a constant multiple of the radius of the ball raised to the power alpha. This slide shows a few different notions of dimension at a glance. We have just talked about Hausdorff dimension. Compare it with the simpler notion of Minkowski dimension, where the covering balls are required to be all of the same scale, delta. Also of importance in this talk is the notion of Fourier dimension. This is defined to be the supremum value of beta between 0 and the ambient dimension n, such that A supports the probability measure mu obeying a Fourier decay condition of order beta. Specifically, the Fourier transform of mu should decay at infinity, like mod z to the power of negative beta over 2. Why do we need so many notions of dimension? The short answer is because they are all distinct and non-equivalent ways of measuring the spread or size of a set. They are tied to each other by the following string of inequalities. The Fourier dimension is always less than or equal to the Hausdorff dimension, which in turn is dominated by the Minkowski dimension. In general, all these inequalities are strict. On one hand, these definitions are intuitive in the sense that they coincide in many cases with our usual notion of dimension borrowed from geometry. Any open set in Rn has dimension n in any of these definitions. A line will always have Hausdorff and Minkowski dimension 1. A plane will always have these dimensions to be 2. On the other hand, these different notions provide a quantitative measurement of size for less regular objects like fractals, with the different definitions trying to capture various properties of these extremely rough objects. The Cantor-Middle third set has Hausdorff dimension log 2 over log 3, but its Fourier dimension is 0. A set A is said to be Salem if its Hausdorff dimension matches its Fourier dimension. Salem sets are widely studied because of their rich structural properties. They are ubiquitous among random sets. Their deterministic constructions do exist, but are harder to find. Here are two more examples. The Sierpinski triangle in the plane has Hausdorff dimension log 3 to the base 2, while the graph of the standard Brownian motion has Hausdorff dimension 3/2. With these definitions behind us, we are ready to state the main results in this talk. This is really our attempt to understand the ramifications of the different notions of dimension. I will come to the precise statements in a moment, but here are the main takeaways. The first result is a comparison between the notions of Hausdorff and Fourier dimensions. Our conclusion is that sets of large Fourier dimension are richer in arithmetic structure. They contain many more rational linear patterns than their corresponding Hausdorff counterparts. The second result is about the kind of patterns enjoyed by sets of large Hausdorff dimension. We show that such sets must contain curved patterns suitably interpreted, but need not contain flat ones. So let's get started on discussing these results in more detail. A theorem of Andras Mathe from 2015 says that there exists a rationally independent subset in the reals of full Hausdorff dimension. In 2017, Schmerkin showed that there is a full dimensional Salem set that avoids all non-trivial arithmetic progressions. This is in contrast with earlier work joint with Isabella Laba that showed that certain Salem sets do contain progressions. The work with Yu Liang was an effort to reconcile these results with her intuition that sets of Fourier dimension are supposed to possess richer structure. The theorem with Liang says the following. In contrast with Mathe's theorem, there cannot be a full dimensional Salem set that is rationally independent. More precisely, if capital E has Fourier dimension larger than 2 over v plus 1, it must contain non-trivial solution of a translation invariant linear equation of this form with integer coefficients and v plus 1 variables. In particular, any set of positive Fourier dimension must have rational dependencies. However, in line with Schmerkin's result, there do exist Salem sets that can avoid solutions of finitely many of these equations, or even certain countably many. Let us go on to the next result, which is joint work with Benjamin Bruce on Hausdorff dimensionality and patterns with curvature. Inspired by the many pattern identification results in the integers, finite fields, and the reals, in 2021, Kuka, Arponen, and Solsten showed a continuous Sarkozy type theorem holds in the plane, and this was the main motivation for our work. They showed that there exists an absolute constant epsilon such that if any planar set K has Hausdorff dimension larger than 2 minus epsilon, then it must contain two distinct points x and y such that their difference lies on the parabola tt square. The nonlinearity of the parabola tt square is critical. The result is known to be false if t squared is replaced by any linear function of t. This is because of the existence of full dimensional graphs in the plane. We wanted to verify the extent to which the work of Kuka, Arponen, and Solsten could be generalized. To that end, let us define the notion of finite type, a concept that is widely used in harmonic analysis as a generalization of non-vanishing curvature. Given a vector-valued smooth function phi in one variable, we say that phi is a finite type at a point t0 if there exists a positive integer capital N such that for all direction vectors u, the projection of phi along u has some non-vanishing derivative of order at most capital N. Phi is said to vanish to finite order at t0 if phi at t0 is 0 and phi is a finite type at t0. To provide some examples, a smooth function phi whose entries are polynomials is of finite type if and only if its coordinate functions are linearly independent. E to the power -1 over t squared is one of the most standard examples of a function that is of infinite type at 0 and vanishes there. Our recent work with Benjamin Bruce establishes a characterization of large Hausdorff dimensional sets in terms of the patterns that they contain. The theorem says the following. Suppose that phi is a smooth function, univariate, vector valued with d entries, vanishing at the origin. If the map t comma phi of t vanishes to finite order at 0, then all Borel sets K in Rd plus 1 of sufficiently large Hausdorff dimension will contain 2 points whose difference is t comma phi of t for some t non-zero. Conversely, suppose that the map t comma phi of t vanishes to infinite order at the origin, then there will exist sets with dimension arbitrarily close to d plus 1 that avoid the pattern t comma phi of t. We are able to prove uniform versions of these statements across certain configuration classes and also extend them more generally in certain directions. But I will not go into these generalizations right now. However, an easy consequence of our theorem is that every finite type pattern of the form t comma phi of t will be represented in every full dimensional set. As you can imagine, the proof techniques that lie behind the many different types of results quoted today are also very different. While it's impossible to encapsulate within the span of a talk the wealth of ideas that have enriched this field, let us take the last 10 minutes to work through a proof which has some representative features and where the main ideas can be sketched without assuming too much background. As an example, let us consider a special case of the result with Liang. We will show that if a set capital E has Fourier dimension strictly larger than 2/3, it must contain a non-trivial solution xyz of some equation of the form tx plus 1 minus ty equals z, where t is a rational number strictly between 0 and 1. Here, non-trivial means that x, y, and z have to be all distinct. The first step in the proof is to answer the question, how do we check for existence of non-trivial solutions to a linear equation? It is quite common in the literature to count configurations by means of a multilinear integral called the configuration integral or configuration measure. In this particular case of this equation, suppose that mu is a probability measure supported on the set capital E. Consider the integral lambda t, which is the average of mu x, mu y, and mu of tx plus 1 minus ty over all x and y in E. One, of course, needs to make sense of this integral, and we do this by rewriting it in terms of the Fourier transform of mu. The decay 1/3 plus epsilon of the Fourier transform at infinity is sufficient to make this integral absolutely convergent. This fact allows us to interpret lambda t as a measure, first by identifying it as a bounded linear functional acting on continuous functions, and then invoking the Riesz representation theorem. We also need to check that the support of lambda t is the set of all solutions of the equation Tx plus 1 minus Ty equals z, and that the mass that it assigns to the trivial solutions is 0. Therefore, if lambda t is a non-trivial measure, in other words, if it has positive mass, then it must signal existence of non-trivial solutions of the desired equation. The second step is to establish that lambda t depends continuously on t, a fact whose proof I will omit, but which is not too difficult to understand in light of the expression of lambda t. A consequence of this continuity is that if lambda t is 0 for all rational t, then it must be 0 for all real t. With this in mind, we proceed with a proof by contradiction. Suppose, if possible, that capital E avoids all non-trivial solutions of trivariate translation invariant linear equations with integer coefficients. In other words, lambda t is 0 for all rational and hence all real t in 0, 1. The main strategy is as follows. We start with the threefold Cartesian product mu x, mu y, and mu z. Since mu is a probability measure, the integral of this product measure is also 1. We now rewrite this measure using a specific permutation of x, y, and z, where x and y are at the two edges and z is in between. This means that we can write z as a convex combination of x and y, with t denoting the convexity parameter. Making a change of variable that replaces z by t, we can write this integral as an average in t of our configuration measures lambda t acting on the bivariate function y minus x. Since all the lambda t measures have been assumed to be 0, this makes this integral 0, which is the contradiction that we have been aiming for. Here is a rough overview of the proof of our result with Ben Bruce, following the methodology of Kuka, Orponen, and Solsten. Let us recall the main result. Suppose that capital K is a set of sufficiently large Hausdorff dimension in D plus 1 dimensional Euclidean space. We wish to show that K must contain a finite type pattern of the form T comma phi of t. Once again, we start with an appropriate configuration integral. This time, it looks like this expression I, where mu is a Frostman measure supported on K, and pi is the induced Lebesgue measure on the curve gamma T phi of t. In other words, I is the convolution of mu and pi averaged with respect to mu. The convolution is supported on the algebraic sum of K and the curve gamma, and the non-vanishing of this integral indicates that this set must have non-trivial intersection with K, which is the desired conclusion. An exciting contribution of the work of Kuka, Orponen, and Solsten is the observation that any set capital K admits a Frostman measure with a spectral gap and that this gap condition is a working substitute for pointwise Fourier decay, which played an important role in previous reincarnations of the problem. I will not be able to describe the construction of such a measure in this talk, but let me at least tell you what the spectral gap condition is. Following KOS, we say that a measure mu obeys the spectral gap condition with large parameters A and B and some small positive epsilon, provided the size of the L2 integral of mu hat in the annulus A to B is at most A to the minus 1 minus epsilon. Let us keep in mind that mu is supported in a sparse set and hence not in L2. So we can only ask for such smallness criteria on fixed scales A and B and not for all A and B. Nonetheless, Kuka-Arponen and Salsten are able to show that it is possible to construct such measures for given AB. Here is how such a condition is used in the proof. The configuration integral I is decomposed into three parts, I1, I2, and I3. An absolutely continuous part I1 at low frequency, a singular part I3 at high frequency, and a last part I2 at an intermediate frequency. I1 is the dominant term and is bounded from below by A to the minus 1. The high frequency term I3 can be expressed in terms of the Fourier transform of mu and of pi. The Fourier transform of pi is of special interest. It is a well-studied oscillatory integral which has non-trivial Fourier decay due to the finite type assumption on gamma. And this is crucial in proving that for a sufficiently large B, I3 is bounded above by a small constant multiple of the energy integral of mu, and therefore can be made much smaller than I1 after choosing B sufficiently large. The part that remains to be controlled is I2, and this is small precisely because of the spectral gap condition. I will not go further into the details of the proof. Let me wind down by mentioning some directions worthy of future pursuit. The open problems in this area are many, but progress has been substantial too. The linear patterns that we investigated form a special class of translation invariant equations, and other types of equations in the translation invariant regime remain to be explored. For sets of large Hausdorff dimension, the results so far extend only to two-point patterns. Advances in this area would involve tackling multi-point configuration integrals using and extending the new methodology that have emerged from the work of Kuka-Arponen and Salsten. Let me stop with that. Thank you for your attention.
Thank you very, very much, Malabika, for this very interesting talk. And I would also like to thank the audience for listening. Unfortunately, we have no time to answer questions, but you can always ask your questions online. Thank you, everybody.
Thank you. Bye.
Woo!